Hello everybody, my name is Iman at SID. Welcome back to my YouTube channel. Today we're going to go ahead and finish the second half of chapter 15. In the first half we talked about the 4 pieces of information, we've covered 3 of them, that you can get from an NMR spectra. We talked about number of signals, chemical shift, and integration. So today we're going to talk about the 4th piece of information that you can extract from NMR, and that is multiplicity. In NMR, peaks tend to have these distinct shapes called the peak multiplicity. Multiplicity, or in other words, coupling, is a view on the environment that a hydrogen resides in. It reveals how many hydrogens are on the next carbon in the structure. So when you look at NMR, multiplicity is defined by the number of peaks in the signal. So 2 questions we should ask about these peaks on multiplicity are: why do we get multiplicity? What is the cause of this peak splitting that we are observing, and what does it ultimately mean? So to answer the first question, a signal's multiplicity is the consequential result of the magnetic effects of neighboring hydrogens. And so then, to answer the second question, it pretty much indicates the number of neighboring protons and allows us to build an understanding of the framework of a molecule. Remember, we can use NMR to get the carbon-hydrogen framework because nuclei with odd numbers of protons or neutrons have something called nuclear spin, and that means that the nucleus rotates and creates a magnetic field around itself called a magnetic moment. When there are other neighboring nuclei like that, then the magnetic effects of each will interact with each other in a molecule. And so a signal's multiplicity is the result of the magnetic effects of neighboring protons, and therefore it indicates the number of neighboring protons. To illustrate this concept, let's consider the following example. All right, if HA and HB are not equivalent to each other, they will both produce different signals. So let's focus on the signal produced by HA, this one right here. In some molecules, all right, HB will be aligned with the field, while in other molecules, HB will be aligned against the field. All right, so as a result, the chemical shift of HA in some molecules will be slightly different than the chemical shift of HA in other molecules because HB might be aligned with or against the field. All right, this results in the appearance of 2 peaks for HA in the presence of HB. So in other words, the presence of HB and the way it may align with the field splits the signal for HA into a doublet. All right, and if you look at the next example, HA, all right, is different than the HBs right nearby. All right, HB here and HB here, they might both align against the field, both align with the field, or mix and match. So there's 3 ways that HB may interact with the magnetic field, and so that splits HA's peak into a triplet. All right, and same goes when there's 3 HBs that are equivalent. They might all align with or against or mix and match. All right, and so that means there are 4 different ways that HB might align with the magnetic field that then splits HA's signal into 4 peaks in its signal. All right, so there are 2 major things that determine whether splitting occurs or not. All right, equivalent protons do not split each other. So when we're looking at HB's signal, all right, all the other HBs that are equivalent to it do not cause the splitting of the HB signal. All right, and splitting is most commonly observed when protons are separated by either 2 or 3 sigma bonds. Now, the way to know what the multiplicity of a hydrogen is, all right, in more simple terms than drawing all the combinations of how neighboring protons may align with or against the field, what you can do instead is count for a specific hydrogen. Say you're interested in knowing what is the peak splitting for the signal of this hydrogen that we've highlighted in red. Well, what you can do is count the number of neighboring hydrogens HA has. All right, this HA has 3 neighboring hydrogens, and then you add one. All right, so if HA has 3 neighboring hydrogens, it's going to have a multiplicity of 3 plus 1, which is 4. All right, and so HA signal will appear as a quartet. All right, so that's another way of doing that. Now, let's put all these pieces that we've learned about NMR together, right? We talked about number of signals, all right, chemical shift, integration, multiplicity. We covered the 4 important pieces of information you can obtain from NMR spectra. All right, so let's do this example problem going through those 4 things just for one specific site even. All right, so if we're looking at this molecule right here, all right, how many unique hydrogen signals are there? All right, we get 1 signal from the methyl group. All right, 1 from this hydrogen, this one, and this one. It has symmetry right through it. So this site is equivalent to this, and then this site is equivalent to this. So we don't want to double count here. All right. So this molecule has 4 unique hydrogen signals that are going to show up. Let's just focus on the methyl here just to demonstrate all 4 aspects of NMR spectra with this one particular example. So methyl, you're only going to get 1 signal for methyl, right? Because all the hydrogens there are equivalent. Fantastic. So 1 signal for the methyl. Let's figure out the chemical shift. Where are we going to find the signal for methyl, all right, for the hydrogens in the methyl group on an NMR spectra, all right? Methyl groups are 0.9 ppm. It's right next to this oxygen. And so that's 3. So we add 0.9 plus 3. All right, we will find the signal for the hydrogens of methyl at 3.9 ppm. All right, 3.9 ppm. It's right there. Fantastic. So we figured out, all right, for our methyl group, where the chemical shift, where the signal will appear on the NMR spectrum. Let's figure out the multiplicity of this signal, all right? So methyl right here, let's draw this just slightly better so we can really take a good look at this. Oxygen, here's the methyl, all right? It's a carbon with 3 hydrogens. I'm going to draw them out, all right? Now, remember, all 3 of these hydrogens are equivalent. So equivalent hydrogens don't cause any splitting, all right? So we want to look over next door. Are there any neighboring hydrogens there? There's not a single neighboring hydrogen to this carbon, to these hydrogens, okay? So these hydrogens have no hydrogen neighbors 1 atom down in this molecule, all right? So they have 0. So we're going to write 0 neighboring hydrogens, and then we always add plus 1 for multiplicity. What that means is the signal for the methyl hydrogens is going to appear as a singlet. So just 1 peak. All right, I can't draw this very well. Just 1 peak. All right, so at 3.9 ppm for our methyl group, all right, for the 3 hydrogens on methyl, the peak is just going to appear as a singlet, just 1 peak. All right, but there's 3 hydrogens there that are equivalent that give off that signal. So whenever you integrate this peak, all right, the integration is going to be 3 hydrogens. 3 hydrogens give this exact same signal back to back to back. But you will only see it as 1, right, because they're all equivalent. All right, so that's how we put all these pieces together. Number of signals, all right? We focused on one group just to demonstrate. We calculated the chemical shift. Where is this signal going to appear on the NMR? All right, what is its multiplicity? Is it going to have peak splitting because of neighboring hydrogens or not? All right, and then the integration. All right, fantastic. Let's do a couple more problems, all right? So this problem asks us, for each of the following compounds, determine the multiplicity of each signal in the expected NMR. All right, so let's do a couple of these just to get the hang of it. All right, let's do A. I don't know why that is B. Let's do A right here. All right, let's draw it out like so. Alrighty, let's figure out the number of signals we're going to expect for this. All right, over here, these 3 hydrogens all going to give off 1 signal. All right, these 2 hydrogens are going to give off 1 signal, 1 signal, 1 signal. All right, we're going to have 4 unique signals to this molecule. All right, we're going to title them A, B, C, D. So let's look at A. All right, let's see what the multiplicity of A is. Okay, so we're going to look at A, we're going to look nearby. All right, does these hydrogens right here, all equivalent on the methyl group, do they have any neighboring hydrogens? All right, so we want to know neighboring hydrogens. We're going to look at this position right here. Are there any hydrogens there? There are no hydrogens. All right, so these hydrogens, these 3 hydrogens right here, they have no neighbors, 0, zit. All right, so we're going to write 0 and then +1 always. All right, so the signal for the 3 hydrogens at position A is going to be a singlet. Fantastic. Let's look at position B. All right, let's look at position B. Right over here, there are 2 hydrogens right here. Okay, we don't count any of them. They're equivalent, so neither of them cause splitting to each other, right? Because they're equivalent. Equivalent hydrogens do not cause splitting. So we want to look over in the neighbors. On this side, do these 2 hydrogens have any neighbors? Neighboring hydrogens. All right, there's no hydrogens on this side. There's no hydrogens bonded to this oxygen at all. And there's no hydrogens in this position either. So these 2 hydrogens, again, have 0 neighbors. We got to add 1. All right, so the signal for these 2 hydrogens at position B is going to be singlet. Fantastic. All right, let's look at C now. All right, let's look at C. All right, there's 2 hydrogens here. Do these 2 hydrogens have any neighbors? Well, we'll look at this side. No hydrogens on that oxygen. Let's look at this side. Are there any hydrogens here? Hell yeah. This is a methyl group with 3 hydrogens. This position has 3 neighboring hydrogens. All right, and then we got to do the +1. So the signal for the hydrogens at position C, all right, whenever we see the signal for these hydrogens right here, all right, the signal multiplicity is going to be 4. All right, so the peak splitting is going to be a quartet, like so, for the 2 hydrogens there. Fantastic. Now, let's do D. All right, do the 3 hydrogens on D have any neighbors? All right, so we're going to look over here. Yeah, they do. They have 2 hydrogens as neighbors. So 2 + 1 is 3. So the peak splitting for hydrogens at position D, whenever you find that signal on the NMR, is going to be a triplet. All right, fantastic. All right, let's do one more. Let's do B. All right, so we're going to go ahead and draw out B right here. All right, we're going to get really good at this. So we have 3 hydrogen. We have 1, 2, 3, 4 hydrogen. 4 hydrogen positions. All right, so we're going to have 4 unique hydrogen signals here. All right, this position is equivalent to this position. All right, so we don't want to double count here. All right, both of them are equivalent. And you can tell they're equivalent because they're bounded to the same things in the same order. All right, so they're exactly the same. So we're not going to double count anything here. All right, so we have 4 positions. We're going to number them 1, 2, 3, 4. All right, let's look at position 1. There are 3 hydrogens at position 1. Do they have any neighbors? We'll look over here. There's no neighbors. All right, so it's going to be the peak for those hydrogens is going to be a singlet. Fantastic. Let's look at position 2. Does position 2 have any neighbors? It does not. So again, it will be a singlet. Fantastic. Let's look at position 3 here. All right, there is only 1 hydrogen here, but how many neighbors does this hydrogen have? Well, let's look. To this side, there are 3 neighboring hydrogens, and on this side, there's 3 more. This hydrogen at position 3 has 6 neighboring hydrogens. All right, so it's going to appear as a septet. All right, 7 peak splits. Alrighty, let's look at let's look at 4, I'm so sorry. All right, 4 only has 1 neighboring hydrogen. All right, so it's going to appear as a doublet. All right, fantastic. Now, the really cool thing about this, all right, we did 2 examples that have really unique signatures that you're gonna see quite a lot, and they're gonna become patterns that you're gonna be able to recognize. All right, recognizing these patterns is gonna allow for more efficient analysis. We saw 2 already. All right, whenever you see, all right, some of these patterns right here, and we're gonna look at them better here. All right, you're gonna know that this NMR is telling you that there's these specific functional groups or these specific types of groups in your molecule. All right, so whenever you see a triplet, all right, with 3 hydrogens right near a quartet with 2 hydrogen integration, all right, this indicates that you have an ethyl group. All right, you could better see it here. All right, here's an ethyl group. All right, these hydrogens have 3 neighboring hydrogens plus 1. All right, that's going to give you a quartet right here. And with an integration of 2, because these are 2 equivalent hydrogens who both have 3 neighboring hydrogens and are going to give a quartet peak. All right, and then when you look at this methyl group, all right, this methyl group has 2 hydrogen neighbors, so 2 plus 1 is going to give you a triplet. All right, so this is the triplet. It's going to have an integration 3, right, because all 3 of these hydrogens are equivalent. So whenever you see a quartet with integration 2 and a triplet with integration 3, know that your NMR is signaling that your molecule has an ethyl group. All right, and we saw that right here. Our molecule had an ethyl group, and we saw the same exact pattern in that example problem. All right, another common one is an isopropyl group. This is what an isopropyl group looks like. All right, we can see it right here. All right, your isopropyl group is going to give off 2 unique signals, right? Because both of these methyls are actually equivalent. All right, so if we look at this molecule, all right, it has 6 neighboring hydrogens. You add 1, it's going to show up as a septet. It's only going to have integration 1 because there's literally just 1 unique hydrogen that has that many neighbors. All right, and then whenever you look at your methyl has only 1 neighbor, so 1 plus 1 is 2, and it's going to appear as a doublet, and its integration is going to be 6, right? Because both of these methyl groups are going to give off that same signal. So the integration for how many hydrogens give off this signal is going to be 6 total. All right, now another really common group that you're going to run across, or pattern that you need to know, is Tert-butyl group. All right, so a Tert-butyl group looks like so. All right, so Tert-butyl group is going to have, right, if you're talking about this methyl group, and this methyl group, right, that's what forms a Tert-butyl group. All of those are equivalent. All right, so all you have to do is consider 1 and look how many neighbors it has. It has 0 neighbors plus 1, so it's going to give off just a singlet. But our integration is going to be 9, right? Because all 3 of these are equivalent. 3 plus 3 plus 3 is 9 hydrogens give off the same exact signal. All right, so these are patterns you really want to keep in mind, because you're going to see a lot of these signatures in your NMR when you're trying to predict molecular structures from NMR. All right, there's one more thing that's not on here that you can refer to this page. There's one more thing that I just want to cover. All right, for aromatic structures, all right, for rings, you're going to find them around 7 ppm, actually anywhere between 6 and 8 ppm really, and they're going to be like a lot of multiple peaks here around that. All right, this is going to signal that you have an aromatic structure, because this refers to aromatic protons. So whenever you get a lot of multiple peaks anywhere between 6 and 8, think about aromatic rings. All right, if it has an integration of 6 hydrogens, then what you have here is an unsubstituted benzene ring. All right? An unsubstituted benzene ring. If you have integration 5, all right, 5 hydrogens for this multiple peaks between 6 and 8, then what you have is a benzene ring that is monosubstituted. So it has some sort of group attached to your ring. All right, and we're going to see some examples of this, but I just wanted to talk about it really quickly. We'll see them in effect into some practice problems, all right? And so now we're going to get into actually a couple practice problems here. Something to keep in mind before we start these problems, all right? Now we're going to start doing some serious investigation of NMR spectra, all right? So trying to draw molecules from NMR spectra, right, that give rise to specific structures. We want to keep a few things in mind when solving these kinds of problems. All right, what we want to keep in mind is sort of how we want to approach these kinds of problems. All right, we will always want to begin by inspecting the molecular formula. It's going to provide us so much information. All right, we can start off specifically by calculating the hydrogen deficiency index, HDI. We covered this in chapter 14. I will refresh your memory with the formula. No worries. All right, so we're going to calculate the hydrogen deficiency index from the molecular formula they give us. All right, this is going to give us some idea of how unsaturated or saturated our molecules are. All right, a hydrogen deficiency index of 0 is going to indicate that our compound has no rings and no pi bonds. That's important to know. All right, a hydrogen deficiency index of 1 is going to indicate that our compound either has 1 ring or 1 pi bond. All right, and the hydrogen deficiency index of 4 or more is going to possibly indicate the presence of an aromatic ring. All right, so those are good numbers to keep in mind. All right, so that's the first thing we're going to do. Investigate the molecular formula as best as we can. Get them as much information from it as we can. All right, then we're going to consider the number of signals we have and the integration of each signal. This is going to give us a lot of information about symmetry or patterns for groups that are present in our molecule, like ethyl groups or Tert-butyl or Isopropyl, right? We just talked about all those patterns, right? So we're going to investigate the signals and integration to get some of that information out of there. Then we're going to analyze each signal, the chemical shift, the integration, the multiplicity, and draw each fragment alone that we can think of. All right, these are our puzzle pieces. All right, and then at the end, we're going to put all these puzzle pieces together to make a molecule structure that makes sense. All right, a molecule structure from our NMR that makes sense. All right. So we're going to go ahead and do a few problems like that. All right, we're going to start off here with A. All right, start off with A. We're going to look at our molecular formula, C9H12. All right, step 1, guys. We're going to calculate the hydrogen deficiency index. The formula for this is 1/2 2C plus 2 plus the amount of nitrogens you have minus the amount of hydrogens you have minus the amount of halogens you have. All right, this is going to be pretty easy. We have only 9 carbons, so 2 times 19, 2 times 9 is 18, sorry. All right, plus 2. We have no nitrogens, we have no halogens, but we have 12 hydrogens, so minus 12. All right, so that's 20 minus 12. All right, that's 8. 8 over 2 is 4. All right, fantastic. A hydrogen index of 4 tells us that we have an aromatic ring. That is so important. All right, we have some sort of aromatic ring. Fantastic. So now let's take a closer look at our NMR spectra here. All right, let's look at this. Let's label this. This is a doublet with integration 6. All right, this is a 1, 2, 3, 4, 5, 6, 7. This is a septet with integration 1. Hold on a second. We've seen this pattern before. All right, a septet with integration 1 and a doublet with integration 2. we know exactly what this is, all right? We know that this is an isopropyl group, all right? So we have an isopropyl group in our structure, okay? So we have an aromatic ring, we have an isopropyl group. Let's look at this last signal. This is a multiplet peak between 6 and 8. We also know what this means. This means that we're dealing with an aromatic ring, all right? But wait, it has an integration of 5, all right? Remember, we said 6 means it's unsubstituted. 5, integration of 5 hydrogens means that this ring is monosubstituted. All right, so we have an isopropyl group and we have a monosubstituted aromatic ring. All right, so we have all the pieces that we need now. Now we have to put all of this together. All right, and the best way we can do this is have the isopropyl group be the one substituent our ring has. So our proposed molecular structure for that NMR is going to be this. Fantastic. All right, so that's for A. All right, let's do one more of these. Then I'm going to leave the other two for you to try to figure out, and I'll try to post the answers for them. All right, so let's do B now. All right, B is a very good one. All right, sorry, lots to erase. Okay, let's do B. All right, we have our molecular formula for B. It's C6H12O2. You know what the first step is? Hydrogen deficiency index. Let's see if we have any rings or pi bonds or what. All right, so 1/2, 2 times carbon plus 2 plus the amount of nitrogens you have minus hydrogens minus halogens. Fantastic. So that is going to be 1/2. 2 times 6 is 12. Plus 2, we don't have any nitrogens, minus 12 hydrogens. Minus 12 hydrogens, we don't have any halogens. Fantastic. So this is going to be 14 minus 12. So 2 over 2. 1. We have a hydrogen deficiency index of 1. All right, so that means we probably have a pi bond or a unsubstituted ring. A ring, a non-aromatic ring. So like something just plain ring. All right, it either means pi bond or ring. All right, we got to keep that in mind as we work through what we have. All right, so that's step 1. Step 2 is to look at what we have going on here and try to see if we can pick out any patterns. All right, here we have a triplet with integration 3. Okay, good. Here we have a doublet with integration 6. Here we have a quartet with integration 2. And here around 5, we have 1, 2, 3, 4, 5, 6, 7 septet with integration 1. Beautiful. There's quite a few patterns here that we should be familiar with, starting off with the septet of integration 1 and doublet with integration 6. We just saw this too. It's fantastic that it reappears. We have a isopropyl group here. Awesome. So we know that our structure has some isopropyl group. Now, we also see another pattern here that we should get familiar with. A quartet with integration 2 and a triplet with integration 3. We know what this is. This is an ethyl group. All right, this is an ethyl group. All right, some sort of ethyl group. All right, fantastic. So we have a isopropyl group. We have an ethyl group. All right, and we know we need some sort of either pi bond or ring, right? Because we have a hydrogen deficiency index of 1. All right, we have a hydrogen deficiency index of 1. Okay, now our molecular formula says that we have 2 oxygens. All right, we have 2 oxygens. So we need to think of a way, all right, to do this appropriately. So maybe as we're playing around, right, we're just putting these pieces together. Our isopropyl group leads straight into our ethyl group. All right, let's sort of play that out. All right. All right, so here's our isopropyl group. Here's our ethyl group. All right, how many carbons is this? 1, 2, 3, 4, 5. We have a total of 6 carbons, so we might need 1 more over here. But we need to make sure that this carbon has no neighboring hydrogens, because if it does, it will ruin our ethyl group. All right, it will ruin our ethyl group. So maybe what's happening here is there's actually a double bond to an oxygen. All right, this would help our ethyl group to not have any neighbors. All right, no neighbors. All right, and maybe there's an alcohol group here. All right, this is just us trying to put the pieces together. We might be wrong. All right, we might be wrong. So what we need to do is double check. All right, so let's double check the groups that we already know first and foremost. All right, here's our ethyl group. All right, let's make sure that all the splitting we have is correct. Okay, here's we have 2 hydrogens here. All right, it has how many neighboring hydrogens over here? 2. All right, so 2 hydrogens right here plus 1. All right, this will give 3. This will give a triplet with integration 2. Okay, and then this one has 2 hydrogens over here. All right, and it has 2 neighbors here and 1 here. So 3 plus 1, that's 4. All right, so a quartet with integration 2. All right, that's interesting. That's not what we see over here. All right, so maybe our proposed structure isn't quite correct yet. So let's go back to the drawing board. That's okay. All right, so what if we have our isopropyl group? What if we have our isopropyl group, all right, leading into a carbon with this 1 pi bond to the oxygen, all right, and then it leads into our ethyl group, and then it leads into our ethyl group, oops, 1, 2, and then an alcohol group. All right, this might work better, right? Because this 2 hydrogens, they have 2 neighboring hydrogens and will appear as a triplet. All right, and this hydrogen has 3 neighbors and appears as a quartet. All right, so sometimes it takes a little bit of playing around to get things that are correct. All right, let's go on to this next problem. This one says propose a structure that is consistent with this NMR. So more of this with a provided molecular formula. All right, so let's look at A. All right, that's this one. And let's write down the molecular formula, C8H10O. All right, now, first step, hydrogen deficiency index. Very important. It's going to tell us if we have any rings or pi bonds. All right, 1/2 2C plus 2 plus N minus hydrogen minus X. Fantastic. So that means 1/2, 2 times 8, 16, plus 2, we don't have any nitrogens, minus 10, and we don't have any halogens. All right, so this is 18 minus 10. That's 8 over 2, and that's 4. All right, hydrogen deficiency index of 4 usually means we have a aromatic ring. All right, so we have to keep that in mind. All right, let's look back at the structure once again. All right, let's integrate this. This hasn't been integrated for us, so let's find the lowest number and divide by it. So 9.1 divided by 9.1, that's 1. This should give us 2. This should also give us about 2, and this should give us 5. All right, so we have a singlet with integration 1, we have a triplet with integration 2, and another triplet with integration 2. This is a common pattern for ethylene. What that means is you have CH2, CH2, and on both sides, they're bonded by variable groups. So that's our first pattern that we need to make sure we write. All right, we have some sort of ethylene group. All right, fantastic. We also have this singlet with integration 1. All right, so we'll keep that in mind. So there's a hydrogen by itself. All right, that could potentially be an alcohol group, especially considering we have an oxygen. All right, so we potentially have an alcohol group here. So let's write that down. Alcohol groups appear usually anywhere between 2 and 5, so this fits that pattern. And then we have this multiplet peak between 6 and 8 with integration of 5. All right, we know we have an aromatic ring because our hydrogen deficiency index told us. And look, we have a multiplet peak to reaffirm that. It has a hydrogen index of 5. All right, so that means it's mono-substituted. All right, so we have a mono-substituted benzene ring, all right, with an ethylene group and a potential alcohol. All right, let's try to put that together in a way that makes sense. All right, let's try to put this together in a way that makes sense. All right, mono-substituted with our ethylene. There's our ethylene. And let's attach that alcohol at the end. This meets all our criteria. So that is the structure for this NMR. Fantastic. Let's do one more for good measure before we move on to carbon NMR. All right, so let's look at this. Molecular formula is C7H14O. All right, hydrogen index is 1/2, 2 times carbon, 14. All right, plus 2 minus the number of hydrogens. All right, so this is 2 over 2. This is 1. All right, 1 hydrogen index. All right, this could usually be a pi bond of some sort or a ring. All right, now let's look at this. We have a doublet. Oh, let's integrate this. It hasn't been integrated for us. So 10 is the lowest number. This will give us 1. And this will give us 10.8. And this will give us 6 about. All right, so we have integration of 1 and 6 here. All right, fantastic. Now, this is a doublet and this is a septet. Okay, awesome. We know what this means. All right, this means isopropyl group. Fantastic. Now, the thing that we need to hold up and check is, all right, we have 1 hydrogen that gives off this septet, and we have 6 hydrogens that give off this doublet for an isopropyl group, but we have a total of 14 hydrogens, and this only tallies up to 7. What this means is actually we have 2 of this. All right, so multiply by 2 and multiply by 2. What we have are 2 isopropyl groups that need to be equivalent, right? Which is the only reason why it doesn't appear as something different. We have 2 isopropyl groups in our molecule. All right, so 2 isopropyl groups that give off some sort of symmetry here, which is why in our integration we don't see it. All right, so we have a pi bond. We have 2 isopropyl groups that are somehow symmetric to each other. All right, we potentially have a carbonyl, right? Because we have this oxygen, we have this pi bond. That kind of makes sense. Let's try to put all these pieces together. All right, 2 isopropyl groups and a carbonyl. They have symmetry, so these 2 isopropyl groups are equivalent. This proposed structure makes sense for what we see in this NMR. All right, sometimes it's going to take trial and error, and that is okay. It's good to kind of try to find all the fragments and put them together at the end. All right, so now we want to move on to carbon NMR. All right, many of the principles that apply to hydrogen NMR is also going to apply to carbon-13 NMR. There are some notable differences that we are going to talk about. All right, for hydrogen 1 NMR, all right, hydrogen 1 is the major isotope for hydrogen. Carbon 13 is not the major isotope for carbon. It's carbon 12. All right, but you can't have an NMR. You can't do NMR with carbon 12, right? Because you need an odd number of protons or neutrons. All right, so carbon 13 is only the minor isotope of carbon, representing about 1.1% of all carbon atoms found in nature. As a result, only 1 in every 100 carbon atoms is actually going to resonate. And so, for carbon 13 NMR, it demands the use of a sensitive receiver coil for it to work. In carbon 13 NMR, we don't need to worry about multiplicity or integration. So good news for you. All we worry about is chemical shift. Why? Well, because no splitting is really observed between neighboring carbon atoms because of the low abundance of carbon 13. All right, we do see carbon-hydrogen splitting, but it's super complex, and actually it's suppressed by broadband decoupling that's part of the spectroscopy instrument itself. All right, the range of frequencies for carbon 13 NMR is between 0 and 220 ppm, so a much larger range than what we saw for our hydrogen NMR. The number of signals in carbon NMR represent the number of carbon atoms in different electronic environments. So here we see the breakdown for carbon NMR spectra and where you would expect to see different groups. So anywhere between 0 and 50 ppm refers to a sp3 hybridized carbon atom like a methyl, a methylene, or a methine group. Anywhere between 50 and 100 can be a carbon triple bond or a carbon nitrogen or oxygen bond. Anywhere between 100 and 150, all right, this refers to a sp2 hybridized carbon. So got to keep that in mind. All right, and then anywhere between 150 and 220, this usually refers to carbonyl groups. So keeping all that in mind, let's quickly jump into some practice problems for this because it's going to be the best way to kind of get accommodated to the differences between carbon and hydrogen NMR. Fantastic. So let's do this. For each of the following compounds, predict the number of signals and location of each signal in the carbon 13 NMR. All right, we're going to do a few of these. Let's look at A. How many signals can we predict for this? Alrighty. Okay, so this carbon will give off one signal. This carbon will give off one signal. This carbon will give off one signal. These two methyl groups at the end are equivalent, so only one unique signal. All right, this structure is going to give off 4 carbon signals. All right, this carbonyl group is going to show up between 150 and 220 ppm because it's a carbonyl. All right, this is a CH2, this is a CH, and this is a CH3. All our sp3 hybridized carbons are going to show up anywhere between 0 and 50 ppm. So we're going to have 3 of our signals between 0 and 50, and we're going to have 1 signal between 150 and 220 ppm. All right, let's do B now. Ooh, that's ugly. Let's try that again. Alrighty. So here's this molecule. This molecule has some symmetry. All right, so we got to be careful when counting the number of signals. All right, so this carbon will give off 1 signal, 2, 3, 4, 5. All right, so there are 5 unique carbon signals here. They're all sp3 hybridized signals here. All right, so they're all going to show up between 0 and 50 ppm. All right, I'm going to let you do D and E, and I will post the answers for that. Fantastic. So with that, let's talk about a little more about carbon 13 NMR. All right, so a broadband decoupled carbon 13 spectrum is not going to provide any information regarding the number of hydrogens attached to each carbon atom in a compound. So simply just having a broadband decoupled carbon-13 spectra like this, all right, is not going to give you enough information for you to look at a broadband decoupled carbon-13 spectrum and know how many hydrogens are really attached to each carbon. All right, but this information can actually be obtained through a variety of recently developed techniques, one of them being Det-13 Carbon NMR, all right, where Det stands for distortionless enhancement bipolarization transfer. All right, so we're not going to talk about why this works, but what we're going to say is to maximize the information obtained, all right, for the carbon/hydrogen environment. All right, so you're going to first do a regular broadband decoupled carbon-13 NMR, and you're going to get the spectrum for that, and it's acquired. And then what you're going to do is a special pulse sequence is utilized to produce this spectrum called Det-90, all right, in which only the signals for carbon-hydrogen groups are going to be obtained. So the cool thing about this additional pulse sequence is it's going to tell you if there's any carbon bonded to a single hydrogen. All right, it's going to give you information about those kinds of groups. And then what you can do is a different pulse sequence is employed called Det-135 that's going to tell you if there's CH3, CH2, or CH groups. All right, where CH3 and CH2 groups appear as positive pulses and CH2 appears as a negative signal. All right, so when you couple these three things together, you're going to maximize the amount of information you're going to obtain about carbon-hydrogen environments, and you're going to be able to predict molecular structure from these three. So you first run a broadband decoupled NMR, carbon-13 NMR. All right, you can get peaks for all of these. They're going to appear between 0 and 50 ppm. All right, but you're not going to know any of these signals between 0 and 50 ppm. Are they CH3 groups? Are they CH2 groups? Are they just carbon-hydrogen groups? Or just a carbon with 4 different variable groups without any hydrogens? You're not going to be able to distinguish that between 0 and 50 ppm on a normal broadband decoupled carbon-13 NMR spectra. So then you're going to have to run some different pulse sequences, right, called Det-90 and Det-135. Det-90 is going to give you only positive peak if there is just a carbon-hydrogen bond, all right? And then you're going to run a Det-135, all right, to help you identify, are there CH3 groups? Are there CH2 groups? You're going to confirm if you have a CH group, or confirm if you only have a carbon with 4 variable groups attached. All right, this is the best way we're going to understand this is by doing some practice problems. So let's jump in to this first practice problem. All right, what we're going to do here is we're going to determine the structure of a compound with molecular formula C5H10O. All right, what we have here is our broadband decoupled and our Det-135. The Det-90 spectrum has no signals. All right, that's important to know. So we're going to start off with our hydrogen deficiency index. Going to be 1/2, 2 times the number of carbon, so 10, plus 2 minus the number of hydrogens. All right, so what we have is 12 minus 10, so 2 over 2, that's going to be 1. So we probably have some sort of pi bond here, and guess what? We have a signal between 150 and 220. That's a carbonyl group. Great, we figured that out very quickly. Now, there are 4 different carbon groups between 0 and 50 ppm. So we're going to need to figure out what those are. All right, so we're going to go one by one. In our broadband decoupled, we have a positive up peak here. All right, we have a positive up peak here. Then we have nothing in the Det-90, and then another positive peak again in our Det-135. That is a CH3 group. All right, so we have one CH3 group for that first peak right here. Fantastic. That's good to know. Let's look at our second group right here. All right, we have a positive peak in our broadband, okay? Nothing in our det 90, and then a negative peak in our 135. That indicates a CH2 group. So for signal 2, we have a CH2 group. All right, then again, for this third peak, we have positive, nothing for 90, and then positive again for 135. That is, again, just a CH3 group. And then for our fourth signal, we have positive peak for broadband decoupled, nothing for 90, and then a negative peak again for 135. So we have another CH2 group. What we have here is a CH3 group, all right? Two CH3 groups, two CH2 groups, and a carbonyl. So let's put this together. Here's our CH3 group, CH2, CH2. All right, let's put our carbonyl here and then end it off with another CH3. We have a CH3, a CH3 here. All right, that's our two CH3s, check, check. We have our two CH2s, check, check. And we have our carbonyl group. This proposed structure makes sense with all the information that we have. All right, let's do one last problem for good measure. All right, determine the structure of an alcohol with the molecular formula C5H12O. All right, we know we have an alcohol group. It does a good job of telling us that. All right, so let's do our hydrogen deficiency index. All right, 1/2, 2 times the amount of carbon plus 2 minus 12 for number of hydrogens. This is simply 0. We don't have any saturation here. Fantastic. We have an alcohol group. We have no pi bonds or rings because our hydrogen deficiency index is 0. Now what we want to look at is this information they've given us. All right. They've told us that we have this broadband decoupled peak at 73.8 that we also see again in our det 90 and again as a positive signal in our 135. So positive signal broadband, positive signal in 90, and positive signal in our det 135. Okay, so this is going to be a CH group. All right, so a carbon with one hydrogen, all right, and some other groups attached to it. Now, recognize the number that the CH group is at. It's outside the range of 0 to 50, which would indicate that it would simply just be a CH group. All right, this is the range where we start to find carbon-nitrogen bonds, carbon-triple bonds, or carbon-oxygen bonds. There's no nitrogen in our molecular formula. Our hydrogen deficiency index is 0, so there are no pi bonds. This carbon has to also be attached to an oxygen, probably that alcohol group that we know our molecule has. All right, so we figured out a very important part of our structure right here. All right, this is going to be fundamental. Okay, so we have to keep this in mind as we figure out the other two groups we have. All right, we have a peak at 29.1, positive peak in our broadband decoupled, and it appears again at 135 in our det 135 as a negative signal. So positive, nothing in our 90 there, and then negative in our 135. We have a CH2 group. Fantastic. We have a CH2 group. All right, and then our last signal at 9.5 appears as a positive peak in our broadband, nothing in our 90, and then again as a positive peak in our 135. That's a CH3 group. Beautiful. So we have a carbon that's going to be bonded to a hydrogen and an alcohol group. All right, and then it has a variable group of a CH2 and a CH3. All right, but that's not enough carbons. We have 5 carbons. This is only accounts for 1, 2, 3 carbons. What this means is our molecule is probably symmetric, which is why we're not getting any more unique signals. All right, So what that means is probably on the same side, we have another CH2 group and CH3 group. All right, so let's properly draw this again and double check if we're actually right. All right, so what we have is a CH3 group, CH2, CH3, CH2, and then our alcohol group is right here. And of course, this carbon has its hydrogen, but we're not going to explicitly draw that in the proper molecular structure. All right, this has 1, 2, 3, 4, 5 carbons, check. It has 3, 6, 8, 10, 11, 12 hydrogens, check, and that oxygen. It has that alcohol group, it told us. All right, everything here makes sense in regards to our proposed molecular structure. All right, so the structure for all this information is this right here. All right, now the best way to learn all of this at the end of the day is just to do so many practice problems. So continue to do that with the homework your professor gives and with all the practice problems you can find in your textbook. All right, get used to this. It takes a while. NMR is probably the topic that is the hardest in organic chemistry to get acquainted with. So continue to do practice problems. If you want to see more problem sets for chapter 15, let me know. Send me your problems and I can try to make a problem set video specifically for chapter 15. Other than that, good luck and happy studying.